Welcome to these lectures on fluid mechanics. As we discussed in the last class, fluid at rest or fluid statics, we have derived basic equations of fluid statics, that is what the pressure equations with related to gravity field. So, now just we will have two applications of the fluid at rest or hydrostatic pressure distributions, that what I will address as applications to two cases. One is manometers, another is for a inclined surface, a submerged inclined surface. What could be the pressure distributions, what could be the total pressure force acting on that plane, also the center of pressures. As again I want to highlight it that you just refer these books starting from Sinjal Simbala, F.M. White and the Fluid Mechanics by Vidyasagar Pani. In the last class, as you know it, we discuss about fluid at the rest. That is what I will have a recap. Then I will talk about the manometers and then we will talk about differential manometer. And I will give you very interesting examples of the stepped weld, which was designed long back by ancient architect, and how they have designed the step weld, and that what we will discuss it. Then we will have the applications of hydrostatics, that to find out the forces on the submerged surfaces, and we will have the summary of this. In the last class, is just to have these things, that we derive the pressure force acting on the fluid and or the control volume, and also we know it how the pressures, the hydrostatic pressure distributions, it just varies along the z directions when you simplify the problems, and on a horizontal surface the pressure becomes constant. So, those the hypothesis we will use it now for derive the equations for manometers or the inclined submerged surfaces. And also we have told you that how simple capillarity effect is considered for a mercury and the tube to measure the atmospheric pressures, that is a barometers, and how this capillarity effect also we computed using the control volume concept, not the simple equating the force components. That is what we discuss it, and the Pascal's law as thinks that all pressure at all the point in all the directions is the same when fluid is at the rest. That means pressure is a scalar quantity, does not have the directions, and the capillarity concept what we discuss it with respect to the surface tension. Now, let us come to the manometer. Very simple devices is used to measure the pressures, like you have let have this type of conduit, the pipes, the carrying any liquids, and you want to measure it, what could be the pressures, pressure on that 5 dimensions. So, we can just insert the tubes, like if you can see, can have the tube like this, or can have a tube like this with inclined and all, or you can have a inclined like this. So, each one having the merit and also disadvantage. Like for examples, the manometer is simple device, that is what use a liquid columns to measure the pressure between 2 points. Okay. So, in this case we are measuring the pressures at for these the conduit, the pipes, using just a simple manometers or liquid columns to measure the pressures. So, you can see that when a simple step form is a piezometers, what is a showing it here is a piezometers, and to find out the pressures, if you know it, pressure at this point is P atmospheres, P equal to P atmospheres. If I taking a point P here, and this dimension is very small as compared to the length of height of this piezometer column. So, if it is that this P A the pressure on this conduct will be the atmospheric pressures, then weight of this column. That what will be the per unit area, that what will become as rho g h. If is height of the column what we got it h, then the pressure at this conduit will be the atmospheric pressure, that is what is acting on this, and the rho g h will be the pressure what will measure. So, if you just measure the height, you can find out what will be the pressure on this pipe what is going through that. Similar way you can have a inclined one or just a vertical one, or the having this concept of the half rectangular case. See, if you look at that, in case of the inclined one, that if I have the inclined length is L, that means the height of the liquid rise is h equal to L sin theta, simple projections. Okay, sin theta will be the projections part of this incline, that what we have a h equal to L sin theta. But sometimes we use the U tube manometers. That means we do not insert just a columns, we make a U shape manometer, we make it U shape, and we also put different fluid on this. So, like for examples, we will have a different the liquid like a heavier or the lighter than this the fluid what is carrying by these pipes. So, what do we have? We have a manometric liquid, and we use a U tube concept. Okay, is just a U shape. We consider as a U tube, and then if this is the conditions, if you look at that, I am to find out what is the pressure is acting on this surface, which is a PA pressure at the centroid of the pipe. See, if it is that conditions, and this is the what is carrying a liquid which is having the density rho, and the manometric liquid having a distance rho 1, if I take this surface, if you look at, if I take this surface as the fluids are at rest, you can understand it, the pressure at this point and this point should be equal. As when fluid is at the rest, if you take a horizontal surface, on that horizontal surface any point you consider, that pressure will be equal. So, the same concept we are using it, that if I take this surface which is the interface between these two liquids, I will have the pressures will be the same. So, if the pressure at these 2 points are same, I can just equate it in this case, like if you are looking at pressure at this point will be the P atmosphere plus rho 1 G H1, that is what the pressure at this point. Similar way, pressure at this point will be the PA rho G H. Rho is the density of the water, density of the liquid what is carrying by this pipe, and G and the height what will be observed in this case. So, you have H here, H1 H. So, if I know measurement of these two height and the density of the liquid what carrying by the pipe, also the density of the liquid which is used as a manometric liquid, then I can compute it what will be the pressure P at this. So, most of the times we use a simple device of this type of U tube manometers to measure what will be the H and H1 with a graduated scales, and measuring this H and H1 and using the simple hydrostatic equations we can compute the PA value. Another case, let me have a inclined manometers, which is have a quite advantage in the sense that it's amplify the pressure reading as compared when you talking about low pressure ranges. When you are measuring the low pressure ranges, being it's inclined, so it's give a easier for us to measure the low pressures as compared to the vertical one. So, now if you look at, if I have this arrangement, this is the conduit where the pressure I want to measure it, which is having pressure P, and this is the conduit is carrying the liquid which is having density rho, and this is a manometric liquid which is having a density rho 1, and because of these pressures, we are getting the H1 of the inclined distance along these directions, and the H is the distance from this P point and this manometric liquid, the interface between this manometric liquid and the carrying liquid by these pipes. If that is the conditions, along again in these direct locations, I have to equate the pressures. So, as you know it, the pressure at this point and these points will be the same as it is a horizontal plane. So, pressure at the O, if you take it the vertical tube, will be pressure at P at this point, rho g h. The very simple things has come up here. For pressure for inclined tube, we have considered H1 sin theta, but the vertical projections part, as it is inclined at theta degree, and rho 1 is a manometric liquid GH, and at this point we have the pressure equal to the atmospheric pressures. So, we get the pressure P naught. Equating these two, we will get these equations which we used to compute what will be the pressure at this point. So, in this case, because you are measuring H1 which is inclined, so that is the reasons the low pressure we can measure it, because we will have a more the length graduated as compared to the vertical case. Otherwise, this is similar way to measure these things, but inclined manometers help us to measure the low pressure readings, because it amplify pressure reading as it amplify the case. As you remember it, the wind tunnel what I have shown to you in the third class, that is what the inclined manometers used in tunnel to measure the pressures. So, this is the same concept of the inclined manometers, that what used to measure the low pressures things, and which is very easy. Just we are considering the horizontal surface which is the interface between the two liquids, and then you are just equating the pressure at these 2 points to get it what will be the pressures at the P point. That what we are looking at, which is very easy, just to have remember this concept, considering this the surface, horizontal surface, then equate the pressure part. But only you have to look at that when you are going down, use a positive sign, or if you are going up, use a negative sign. That the very basic concept here, that if you have a pressure P here, my point is here, which is distance between these, the height difference is h. So, I will have use a positive things plus rho g h to compute this. If it is below that, I will use a negative thing, or h can consider as a negative value, and that what will be use it to this one. So, only you have to remember it to consider a horizontal surface, and most of the time you consider horizontal surface, that is a interface between two liquids, and at that location's surface you just equate the pressures at the 2 points to derive the pressure equations. And once you know the pressure equations, as you will have a measurement of H1 and H as a graduated scale if you have, then you know the sin theta, you know the density, and you know the atmospheric pressure, you can measure what will be the pressures on these pipe carrying any oil, other waters. So, you can measure it what could be the pressures at that point. Now, there is another type of manometers which is called the differential manometers. As the name says that here we do not measure a particular point pressure measurements, where you consider 2 points, because many of our applications we are not worried about absolute pressures. Mostly we are looking at the 2 points, like I have the pipe and I have the point A and B. So, this is a pipe flow, I have the point A and B. At these A and B locations, I want to know what is the pressure difference between these 2 points of A and B in this pipe flow. I am not worried about the absolute pressure at the A or the absolute pressure B. I want to looking for a relative pressure between these two difference between these 2 points. That means I am looking the difference between PA minus PB, which is driving the flow from one side to the other side. I am just looking at what is the difference pressure between that. So, that means we use differential manometers which measure the difference of pressure between 2 points in a fluid systems. That is what I said, that it does not measure the actual pressures of any point of the systems, it is a differential pressures. When any 2 point of a system, we can attach these manometers to measure the pressure difference between a PA and the PV, that the difference we are measuring. It has also a very simple U tube connected to these 2 locations. Like this case, I have the 2 pipes, let be a P A and B, and we are to look at the pressure difference between the P and PB. And this is what the manometer is attached to these 2 flow systems. If it is that the conditions, and consider these tools are carrying the same the different liquids. Okay. They are carrying the different liquid having the different density like rho 2 and rho 3, and rho 1 is the manometric density of the manometric liquid. Okay. If this is the arrangement, and you measure the distance from these flow systems, and these manometers becomes equilibriums after this certain flow, that then we measure the distance H2, H3 and H1. Now, I can write on the surface of AA, okay, on the surface of AA, I can equate the pressures, because as I already told you that pressure along the surface will be the same. So, if I start that once, from this side will be the PB rho 2 G H2, that is very clear cut. The pressure will be this way. If I go it, PB is a pressure at this point, then difference will be the rho G, rho 2 G, that is the density of these ones, G and H2. If I look at this point, the pressure limb which is connected to a part will be the PA pressure at that point. Then because of the fluid what is carried by this conduit, you have a H3 is the height, which will be rho 3 G H3. Then you have a manometric height liquid, the difference which will be a rho 1 G H1. So, you will get the these very basic equations to compute the pressure difference. So, you can finally make it what is a PA minus PV, that what you can simplify it, or you need not to remember any things. You take appropriate horizontal surface at the interface, then just equate it the pressures as I go down from PB plus rho GH, the weight of the fluid will come it. Similar way, I start from PA, the weight of the fluid of this part, the weight of the fluid of this part, if I combine it, the pressure will come it here. When we are talking that, we are per unit area we are considering. So, that is the reasons we have a rho 3 G H3, rho 1 G H1. So, these 2 terms comes here, and these the terms what it comes from here. So, you can write these simple equations, you need not to remember it, only to know it, that as I am going down, the weight of the fluid liquid you have to consider it when you are going down, and that weight will come it here to per unit area, that weight will be as equivalent to pressures will come it, that what you will add it to at this surface. So, it is very easy way. So, whenever you get a manometric applications problems, first you choose which one should be appropriate the surface where you can write the pressure equations. So, if you know that one, then you can solve these problems easily, it is not that difficult ones. Now, if you look at, if I have a inverted U tube manometers, okay, that is inverted cases, okay, this is the manometers. When you use the manometer fluid, you use in this type of manometer is lighter than the working fluid. So, these are the working fluid which is having this rho 1 and rho 3 are 2 different density of the working fluid, but rho 2 is the density of manometric fluid. And here this manometric fluids having the lighter than the working fluid. That means the rho 2 is a less than rho 1 and rho 2 is less than the rho 3. Okay. So, these are very less as compared to this, then we need to have an inverted case. So, as it is an inverted case, and if I consider a surface, like I am considering this is what the surface for me. Okay. Here if you look it, we have to consider negative surface, because when you have the PA here, you can use rho 1 G H1, but it is a negative because it is going off as compared to weight is, we are losing that weight which is against of that the pressure part. Okay. So, that way PA rho 1 G H1, this negative is coming it. Similar way, if you start from PB, you will have a minus rho 2 G GH2, this part, then you will have a this part. So, either you can put it here or here, it does not matter it. So, you can write these pressure equations for a inverted U-tube manometers, the considering this is the surface where you are equating the pressure, which is the, you can consider any other location, that does not matter it, only you have to a sign convention whether this working fluid, the positive and negative sign of H you can consider to solve the problems. So, where you have to consider this point, it does not matter it, you can solve the problems, but you can know it which one will give a simplified the case, like the surface what you consider it, and you can. So, in case of U-tube manometer which is inverted one, then we use the same equations, only this negative terms are comes it, the because we it is a U-tube inverted one, we go off to measure the pressures on that surface as compared to the working fluid which is a lower than that. So, because that is the reason is a lighter fluid as compared to the working fluid. So, manometric fluids are lighter, which is a inverted shapes, then you have this. So, we have to measure like this. Now, there are a simplified micrometer manometers are there, which is measure the pressure difference between A and the B, and you have the flow. This flow may be carrying oil, or may be carrying slurry, may be carrying any industrial use. If you look at the any industry is a lot of pipe networks, and we have to measure the pressure difference between 2 points, which is required to measure the discharge, measure the frictional losses and all. That what we will discuss in later on classes, end of these courses. So, basically we want to measure the pressure between these 2 points, PA and the PB. What we do it? We use a reservoir here, okay, it is bigger, then a inclined part. Then we have a flexible tube which is connected to between point A and the reservoirs, another flexible tube connecting the point B, other end of the reservoir. So, you have the tubes, you connected it that once, and there will be a reference mark R will be there here, okay, and this level of the pressures is moved such with that this level will be the reference mark. You can put it as reference mark. Here what will be there, when the flow will be there, there will be a pressure difference. That pressure difference will be cause the difference in the height of this case. And this mechanical screw arrangement with a pressure reading as equivalent as the screw goes up and down, the what could be the as equivalent to pressure, that what is written on this graduated scale, understand. So, we needed to read this the manometric height level. Here just we rotate the screw till make it the reference level, and that lifting of this reservoir and the screw arrangement will give us a reading at this point, which is the pressure difference between these 2 points. So, it is a simple arrangement with having a reservoir, the inclined one. We can use the pressure equations to solve it, or here to adjust the level of reservoir with help of the screw, and the screw is calibrated with the pressure difference what is graduated here, and as you move it, as you make a screw adjustment for a particular level, then you will have a parallel reading what could be the pressure on this. So, a simple mechanical arrangement with a manometer, with a reservoir and inclined plane, we can measure the pressures with this type of screw arrangement. See, this is what is called micromanometers, that what is used to measure with a micrometer screw, the screw which is the micrometer levels, that what is used for measuring the pressure difference 2 point P and PB locations. Let us come to a very interesting topic on pressure acting on a submerged plane surface. Before going to that, let me give a very interesting examples what we have the steps wells in the western part of our countries, that what is used for rainwater harvestings, and the wells are designed such a way that even if rarest drought period, also the water is available in that period. So, the well was built long way, maybe 2000 years old or more than that, and the depth of the well, it goes beyond 50 meters, 100 meters, and the well is not a serving just for a water, also the wells are used many of the times to have a social gatherings, the programs also they conduct it. So, how they have designed so beautiful well systems in western part of our country. The one of the photographs what I am showing it, the step wells, if you can see it, this is a plan view of the step view, and there are lot of architectural part and there are the peripheral part. So, that means in during these rainy seasons, when you have a high rainfalls, this well get totally filled up. As it dries off during the summer seasons, it goes down and down and down. So, if you look at this, the constructions, how they have considered the hydrostatic pressures when you have a extreme flow conditions, or when you have this well are at the full filled conditions. Like for examples, this well is considered, let be the flood level here. Now, I am not considering so complex geometry what is there. If I consider very simplified geometry what I am sketching it here, these are what there are inclined surface, there are vertical surface, there are maybe curved surface are there, and there are horizontal surface and all. And these water levels, if you can understand it, fluctuates it. Okay. During the summer seasons, it goes down. During the rain season, it goes up. So, it is goes up and down with a seasonal variabilities. And how they have designed it? What is the water pressures? Is acting on this surface, acting on this surface, if it is surface A, surface B, one is horizontal, another is vertical, another is inclined, and could have the curve natures what is there. There are the curve, the projections and all. How much of water pressures you act it when you have a totally the tank wall well is in a filled conditions. Very interestingly, when design it, that means we need to determine what is the pressures force acting on vertical surface, horizontal surface and the inclined surface. For a horizontal surface like what here, it is a very easy. If I have a the fluid rho 1, okay, and height is h3, pressure at this point is P atmosphere, you know it, the pressure at this point will be the P atmospheres plus rho g h3. So, and the pressure distributions will be the uniform as it is the horizontal surface. As it is a horizontal surface, you will have a pressure distribution, it will be uniform, and as the uniform pressure distributions, so it will be act, the maximum force will be act at the centroid of this surface. As the pressure distribution is uniform, the center of pressure or where the pressure force is acting on that center, that what will be the match with the centroid of the surface. The surface can be a circular, can be elliptical shape, but that what will act on that. So, you have the pressures of that. When you have this vertical surface, let me consider this case. Okay. You can find out that, as you know, if this is H1 and this is the H2, so the pressure distributions will be the trapezoidal distributions, because at this point the pressure will commit as rho g H1, at the point pressure will be rho g H2. So, this is the what? Pressure diagram. This is what? The pressure diagram. As the vertically, the rho g H1 is a pressure at this point, and this H2 distance from the top will be rho g H2, and I am neglecting the atmospheric pressure. That what we are neglecting as compared to the pressure what is getting from the water, which is, you know, it much higher value of density as compared to the density of atmosphere pressure at the atmospheres as compared to that. So, we can get the pressure diagram which will be trapezoidal forms, and if I know this pressure diagram, I can compute what will be the total force acting due to this pressure diagram, which is a very simplified things to find out the area of these pressure diagrams. Okay. Multiplied with the perpendicular distance, or that what is many of the time we consider unit distance, then the area of these diagrams will tell me that what is the force is acting because of these pressures. Now, another point is coming it, where does this force act? The locations of this force acting is the center of pressure. That the center of pressures we can compute it very easily, that is what I will demonstrate it to you. But when you have an inclined surface, also we can determine the pressure diagrams, as you can find out the pressure will commit as a similar way trapezoidal part, and the pressure will be normal to this surface, the normal to this inclined surface, and that pressure diagram again you can find out the area of the pressure diagrams, or you do the integrations, that is the same things that you are integrating the pressure diagrams to find out what will be the force acting due to the pressure distributions, or again you look at where is the center of pressure, when at which point this pressure force acts, that is what we look at as a center pressure. And many of the times if you look at this beautiful the wells, step wells, our ancient people they well known about these hydrostatic pressures and all, and they designed the structure which is existing still now without any damage. So, that what indicate us the knowledge on hydrostatics or knowledge on the fluids. Now, if you look at that, let us coming to the derivations of the hydrostatic pressures on a submerged surface. That means surface is a submerged in a liquid. So, we have the atmospheric pressure is on that, we have the free surface, and I am just putting a surface which is the x and y projections in these directions. If you look it from this point, you will have a inclined surface which is having this x and y. This is what very complex shape we have considered it. Okay. And that is what inclined, and is having the h height, and we are looking at what could be the force due to these pressure distributions and where does it act. That is what we are looking at. These two things we know it, then we can design these things, that what type of material to be used, what type of lifting arrangement should be there, if there is this is as equivalent to a gate conditions. The submerged plate can be considered as a gate conditions. So, total force caused by retaining liquid, that what we are looking, and directions and line of actions. As the directions will be always perpendicular to the surface, that what the directions, and the line of actions what of the force is the center of pressures. Now, to derive this part, let me consider a small element. Okay. Let me consider a small element. In this small element of the dA, if the pressure is P, then P into dA will be the force, pressure into area will be force. The negative sign we have considered because considering the normal vectors. If I am considering the press area, that normal vectors and the pressure they have opposite directions. That is the reasons we use the negative sign, the pressure force acts against the surface, because surface normal vectors and pressures they are in opposite direction. Because of that we use the negative signs. Otherwise, the pressure acting on this small area of dA will be the force P into dA is a small elementary area what we have considered to derive what could be the total force acting on this as well as the center of pressures. If you look at that, that means to get a total hydrostatic pressures we have to do a integrations, the area integration, surface integrations of this quantity. Okay. So, if h is a depth, we know it, the depth is a function with the unit weight dP by dH. Substituting that any point the pressure will come it, as we discussed in a manometric case, the pressure at this point will come as pressure atmospheric pressure plus unit weight of the waters or any liquid what we are considering, then the h is the height, is the vertical height what we are considering, that is what the pressure. If you just integrate these equations you will get it this part, that is what is there, and which is we are integrating from 0 to h to get it what is the pressure at this element elemental area of dA. Now, if I integrate this part, if you know it, one component will come it with atmospheric with A, another component will be W sin theta y dA. Just resolving the components, okay, you can get it y into dA. What is the y dA? Very simple things, is a first moment of the surface area about the x axis. If I have this x axis, if you look at this top view, you have the x axis, this is the y axis, this is what? The first, this is the area, I am taking first moment, okay, first moment from this y axis, this is from this x axis, that what the first moment what will come it. So, that means if you integrate this first moment, that means it will become a centroid of yc, that yc distance from x axis, that is the distance along the y directions, that is the centroid point what will be there. If this surface have a centroid, this yc will come it. That means if I just put all these values, what I am getting, this part which is w sin theta yca. If you look at this component and take the A out from this, come on to this, that is what at the center point, at the center gravity point, CG point, at that point we have what is the pressures, that is the PC multiply the area, that what will come is the force. That means if you do integration it is okay, but if you do not do the integrations for any surface, you can find out the total hydrostatic force on a submerged plane, that equal to pressure at the centroid of the area, that is what we have derived it, okay. Centroid of area multiplied with the area of the surface, and as we have discussed earlier, it acts normal to the surface, okay. One is that you can do integrations and find out these things, or if you know the CG, the center of gravity of that submerged plane surface, at that CG point you get what is the pressure, that is what easy to find out what is the pressure, and once you know that pressure multiplied with the area of the submerged space, that what will get is the force component. So, that what you have just to remember it if you want to solve the problems at faster rate, okay, as compared to do a integrations and solve the problems. But be remember that when you have not a single liquid case, like for this case we have a single liquid systems. That means I have the single liquid systems which is easy to do it. But let you have the plate which is having somewhat in the two liquid interfaces. In that case, you have to do the integrations to find out where does it act in. Okay. So, the like in this case what we have considered is a single liquid having the rho 1 constant that, but if you have a multiple liquid, the liquid 1 and liquid 2, they will have a different densities, and find out what is the pressure force acting on this, then you need to do the integrations, find out the element area, integrate it from one liquid another liquid, find the total force acting on that, as the pressure diagrams changes it when you have a two different densities, two different fluids with a different density. So, you will have a different pressure diagrams, and that what you have to consider, and in that case you have to do integration. But if you have a simple one fluid systems, then the density is a constant, then you can find out the Cg. At that Cd point you find out what is the pressures, that what you can just equate it, atmospheric pressure, then height, how, what is the point below the from the free surface. Then you, if you know that the pressure at this point, multiply this area, then what will you get it? The force component. So, force component due to the hydrostatic pressure distribution on a inclined submerged plane can easily obtained following these simple equations. Now, let us compute to that, we need to compute center of pressures. That means, the point of actions of total hydrostatic force on this submerged surface. That is what I try to explain it, that it is not that where this force acted, that is what is also the plays a major role to design a structures. Okay, design a gate, design a any wall, we need to know it where this force, the location of the force also matters, and that is what the center of pressures. That was the center of pressures. Now, if you look at how to compute it, this is a very simple case, as you have done it in case of solid mechanics. You take a moments of resultant forces, the total pressure and the pressure distribution, and take it from one point. Here we consider from a axis of axis point to compute it, what will be the point where it acts it. So, there is a simple problems like as you have done cantilevers with different loading to find out where the point where you have the force is acting it. The same concept we use it to find out the moment of resultant forces about any axis. You can have x axis and y axis, the equal to the moment of distributed force about the same axis. As we do in a solid mechanics, same concept we are using. We know the pressure distributions, there you know the load distributions, and you know it what is the total force acting in. Here also have a total force acting because of this pressure distribution. Then you try to find where it works it, that what to find out the moment of resultant force and moment of the distribution force. That what we do it. That means YCP into F. Okay. YCP, if you look at this figure from the x axis, the distance from the x axis YCP, XCP is this direction, this is the point of Cp, center of pressure will be Y into P into dA, pressure into area force Y dA, we just integrate it to equate this part. So, Y multiplication is there, that what is the any point if you consider that what the moment about the distributed force, what we compute it. It is a simple problem as you did in solid mechanics. If I do that part, do the integrations and all, what I will get it like this force F will be this component as we have derived it, pressure will be we need to it, and H will be the y sin theta, equating all, then what we are getting it that the YCP will be the y square dA, area integral y by dA, that means second moment of area about 0, okay. The first moment of area about O, which is the YDA part. Now, if you use the parallel axis theorems, then you can find out what could be the second moment of area about the central axis, that what I axis I see with compared to the centroid axis at the x axis which is far away from YC distance, that the parallel axis theorems which you know it in solid mechanics. If I use that, then I will get finally these equations. Now, if you look at these equations, that any distributions you will have this component which is additional component, and this is the centroid locations y. Well, this is the YCP. That means the center of pressures always below the centers of a submerged plane. So, if you consider a submerged plane, if you have a CG at this point, your CP is always be lesser than that because of this component mathematically. And if you look at the pressure distributions, you can find out if you have a linearly increasing the pressure distributions, definitely it will not be the force, the resultant force will not act in the CG, it will act below of that to make it the equal portion of the area, equal proportion of the area in both the sides. That what will happen it just below on that. So, that what the graphically you can understand it, mathematically also we can see that with the integrations and all we can compute the YCP will be this component plus the YC.